Hello, welcome to another OVTO webinar. My name is Johan. Today we have a topic for webinar, tissue-based refracture assessment. The speakers for today are Jason Forman and Johan Iraeus. Both of them are OVTO members. Johan also serves as the secretary of on the OVTO committee. For those who may be new to OVTO, the OpenVT organization, let me give you a quick overview. OVTO is a non-profit association dedicated to advancing open science in the field of virtual testing and biomechanics, particularly for road safety. Our mission is to promote research and provide open source tools that support mission to the global goal of eliminating fatalities and serious injuries in traffic. One of our key initiatives is the OpenVT platform, an open and collaborative infrastructure where researchers and developers can share and maintain tools. And recently, we hosted a webinar series where we would like to see it as a platform for presenting tools and methods useful for virtual testing. You might have seen when you signed up, these webinars are recorded for your information. These recordings will be made available on YouTube later on, and that these can serve as open educational resources for researchers and practitioners. It's my pleasure to introduce the speakers for today. Jason Forman is an associate professor of mechanical and aerospace engineering at the University of Virginia Center for Applied Biomechanics. He's a member the board of directors of the Association for the Advancement of Automotive Medicine and is an associate editor of the journal Traffic Injury Prevention. He has over 20 years experience in injury biomechanics research, including the development of injury prediction methods for ATDs and human body models. Our second speaker is Johan Iraeus. He is a researcher at the Division of Vehicle Safety at Chalmers University of Technology. He leads the activities around HBM development at Chalmers. He is one of the early adopters of Forman's tissue-based injury risk framework during his PhD 2010 to 2015, and has continued to use and contributed to the development method, in particular in the context of population variability. Johan is involved in the development of both the SAFER HBM and the VIVA HBMs. Welcome, Jason and Johan. I'm looking forward to hearing from you. Jason, over to you.
Great. Thank you so much, Jobin. Let me get my screen shared properly here. All right. So the work that I'm going to show today has taken place over many years, about the last decade or so. And portions of it were supported by the Toyota Collaborative Safety Research Center and also by Autoliv, for which we greatly appreciate their support. So I'm going to go a little bit quickly to try to keep us on time, but we should have some time for some questions and expansion and Q&A at the very end of the webinar today. So to dive right in, if we think about how to predict injury using information, tissue level information that's output by human body models, so things like local strain or potentially local stress, depending on the application. There's two different ways that we can go about predicting injury using tissue level information. The first way is what's called deterministic. So deterministic is a threshold-based approach where we have a binary criteria where we say if, for example, the strain is below a certain level, there is no fracture or injury. And if the strain exceeds a certain level, then we define that as causing fracture or causing injury. And it can either be a binary yes, no, it could be a element elimination sort of threshold, right, where we actually eliminate the element in the model once the strain is exceeded. It could be a strain softening threshold. But the core concept is that it's binary, it's threshold based. It gives effectively a yes or no answer. And then by that nature, we're really predicting injury for a singular specific type of subject. or person. The alternative would be a probabilistic approach, where instead of setting a threshold, we take the outputs from the model, the strain, for example, and we compare them against a continuous probability function. So we have output of the model. Here it's labeled input, so the input into the function. And then we have a continuous curve that tells us a probability of injury given that level of measure. Let's see. Jobin just asked if he could hear me. Can everyone else hear me? Can somebody? Okay, Johan says
I can hear you. Yeah.
Okay, excellent. Okay, very good. So I'm going to continue on. Jobin may be having connection issues.
No, it was for someone else, so I didn't mean to ping you. Please go ahead.
I'll continue.
Yes, please continue.
Very good. So FE-based or finite element-based probabilistic prediction is not a new concept. It's used in other engineering disciplines for mechanical failure analysis and risk analysis. And over the past 10 years or so, it's gained adoption in injury biomechanics as well. All right, so what does that look like on a basic level? So we're going to talk about ribs and rib strain. So the rib cage is a bit of a unique problem in that we have 24 different structures within the rib cage, 25 if you want to count the sternum. But let's say we have 24 individual ribs, 12 on each side. For each one of those ribs, we can run a simulation, a crash simulation, and output the peak strain. And there's a lot of different ways to output peak strain that maybe Johan will talk about a little bit later. But for now, let's just say peak strain in general. So for each rib, we output some measure of peak strain. We can take each of those individual peak strains and compare them against a local risk function. So here's a function that Johan will talk about, developed by Callie Larson, where we have strain measured in the rib, and we can input that into the function and output the risk of fracture in that rib. And this function is nice because it also allows us to adjust for age. But let's say we take each of these individual strains, we input them into the risk function, and then we output a probability of fracture in each rib for a particular chosen age. And we end up with a series of risk values, right? Risk of fracture in each individual rib. So for the rib cage, it would be 24, but we're just listing it down to a generic total number n, right? So n probability values. That's all well and good. But from a utility standpoint and from a engineering standpoint, it's maybe not quite very useful, right? Because if we have 24 individual probability values, it's hard to wrap our heads around what exactly to do with that from an assessment standpoint. So we still have a lot of information to work with here. So what can we do with it? Well, the approach that we proposed a number of years ago is effectively a combined probability approach. To illustrate what that is, we're going to walk through a simple example, starting with flipping a coin, right? So if we take a coin, a regular coin, and we flip it once, we have a 50% probability that it will land heads up, right? So one flip, what's the probability of having it land heads up in that one flip? 50%. Easy enough. All right, so what happens if we flip it twice, right? The same coin, a fair coin. So for each flip, it has a 50% chance of landing heads up, right? So flip number one, 50% chance of heads up. Flip number two, 50% chance of heads up. So let's look at an outcome table, right? So now we have in the top here, we have some potential outcomes for that first flip landing, a heads up, 50% chance versus heads down, 50% chance. And then in the rows here, we have the outcome for flip two, right? So again, 50% heads up, 50% heads down. But we want to know what are the various combinations that can happen, right? So for example, what's the chance that we would have flip number one land up and flip number two also land up? Well, you can determine that chance by multiplying those two individual probabilities together. So we have a 25% chance that both flips would land heads up, and so on. You can fill in each of these outcome chances by multiplying the probability of that particular outcome for each of the independent events, right? So 25% chance in each of these potential outcomes. All right, so now we want to ask the question, what's the probability of having exactly two heads up, right? So flip one and flip two landing up. Well, we just look in that cell, 25% chance, right? What's the probability of exactly zero heads up, right? So they both land heads down. Again, we can look in this cell. It's the chance that flip one would land down multiplied by the chance that flip two would land heads down. So 25% chance there as well. All right, we're going to get more complicated. So what's the probability of having exactly one heads up? So now we have two potential outcomes that satisfy that criteria, right? Either one down and two up, or one up and two down, right? So now we have two different outcomes that satisfy that target outcome criteria that we're seeking, right? So we add those two probabilities together, 25 plus 25 equals 50% total chance that we would have exactly one heads up out of those outcomes. All right, now what's the chance that we would have at least one heads up, right? So now we're looking at an inequality. So now we have a bunch of different outcomes that could satisfy that target outcome that we're seeking to understand. We could have both coins land heads up, so we have a 25% chance there. We could have one or the other coins land heads up, so those two cells also satisfy that criteria. The only one that doesn't is this all heads down case down here in the bottom right. So the probability of having at least one coin land heads up is these cells added together, those outcomes added together, 75%. The other way that we can calculate that, slightly more simple, is by looking at the opposite. What is the chance that we would have no cases land heads up, probability of 0, and we just take the inverse of that. So 1 minus that alternative outcome, 1 minus 25% gives us the same answer. So I'm seeing in the chat that some folks are having a problem hearing. Not quite sure what to do about it. If you guys can, okay, so I'm seeing some positive feedback as well. So I'm going to keep going. If it ends up being systematically bad, everyone flood the chat and we'll pause and figure out what to do.
I think it's okay for most, Jason.
Okay, very good. All right, so that's the basic concept, right? So basic combinations of potential outcomes. We can add a layer of complexity on there. So what if it's an unfair coin, right? A weighted coin where we have a slightly higher chance of any flip landing heads up, right? So 60% chance of landing heads up on any flip. So we can fill in the same outcome table just with the revised probabilities there. So now for any flip to land heads up, for any flip, we would have a 60% chance of landing heads up, right? But we can run the same analysis where for any of these potential outcomes, we can calculate the chance of that outcome by multiplying the chance of that outcome for each combination of probabilities, right? So 36% chance of 2 heads up, right? And so on, right? But we can run through the same chain. And we can go even more complex where we look at 2 different coins where now the probability of heads up is unique for coin number 1 compared to coin number 2. So for coin number 1, we have a 60% chance of heads up, right? So if we look at our outcome table, we can look at the risk of having coin 1 land heads up versus coin 1 landing heads down. That would be a 40% probability. Coin number 2 is different in this case. It has a lower chance of landing heads up, right? But we can fill that into our outcome table as well. All we're doing is multiplying probabilities for each individual event to look at the probability of any combination of those events occurring, right? But it's the same chain of reasoning. Then we can start stacking on more and more events, right? So more and more coin flips. So this is where it gets a little bit complicated. We go beyond 2 by 2, but the math is exactly the same, right? So now we have a whole bunch of different coins or a whole bunch of independent measures of probability, right? From 0% chance of something occurring down to 100% chance of that thing occurring. But the core is we have a stack of individual probabilities of outcomes for specific events. And we can combine all those individual probabilities in order to calculate what's the probability of exactly one event occurring, what's the probability of exactly two positive events occurring. We can convert it into our inequality, right? So from this string of probabilities, we can calculate the probability of exactly a chosen number of the outcome happening that we're seeking to predict. We can also, again, like our coin flip, we can turn that into an inequality and calculate the probability of one or more of the thing happening, two or more of the thing happening, three or more of the thing happening, etc. Now we talked about coins, but this should look a lot like our rib fracture problem, right? With the rib fractures, we have the exact same type of information. We've taken strain and we've used it to calculate the probability of fractures in each individual rib. But we can use that information in the same way to calculate what's the probability of exactly one rib fracture occurring, right? So think back to our coin flip analogy. What's the probability of exactly two rib fractures occurring? What's the probability of exactly three rib fractures occurring? And we do that using what's called a Poisson binomial model, all right? So this is the same combinatoric approach that we just went through with our outcome table. It's just putting it in math form and allowing the complexity to have a large number of probability observations. So n probability observations, n total ribs, if you will, and then a chosen number of outcomes that we're targeting. So x incidences of the coin landing heads up, x rib fractures, right? And I won't go through the math with this. It's there. It ends up getting numerically a bit cumbersome because you have to brute force run through many, many, many different combinations to calculate the total joint probability of the number of ways that you could have 3 rib fractures or 4 rib fractures or whatever it is that you're seeking to predict. And then we can also turn that into our inequality as well. That actually ends up being a little bit simpler. Once you know the probability of exactly 1 fracture, the probability of exactly 2 fractures, etc., effectively you just add those up, right? Or you look at the inverse. So you can see the probability of 1 or more fractures just by taking 1 minus the probability of exactly 0 rib fractures, right? So that's the workflow. So from a simulation, we can take the peak strains in each rib. We can compare those peak strains against a local risk function, right, to get a risk of fracture in each individual rib. We can run that through our Poisson binomial model, right, with a target number of rib fractures that we're seeking to predict. So 1, 2, 3 rib fractures, whatever the target is. Stack them up using our inequality, and then that can give you the probability of 1 or more, probability of 2 or more, etc. So I'll give you a quick example of what this looks like. So this is an early just exemplar simulation that we ran with the GHBMC in a very simplified load case. The details don't matter as much here as just illustrating the overall information that you can get out of this approach. So this is a 20 kilometer per hour frontal sled simulation. We've output strains, ran them through our algorithm. And in this particular case, we're predicting 69% chance of one or more rib fractures. If we take a deterministic approach and set a reasonably logical strain threshold, in this case, we were predicting 0 rib fractures. If we run that same simulation at 30 kilometers per hour, we see our distribution of risk for different levels of rib fracture change. So now we're seeing a higher risk of 2 fractures, 2 or more rib fractures, and that falls off lesser probability of greater numbers of rib fractures. And our deterministic approach shows us something similar, where we happen to exceed our target strain threshold for 2 ribs, so 2 fractures. And you can see how it progresses if you increase in overall test severity, so 40 kilometers per hour. Now we see a high risk of 4 or more rib fractures, right? And that's consistent with our deterministic outcome. And we can also use this sort of information to look at time history. So now we have our 40 kilometer per hour simulation. So one singular simulation. We've output time histories of rib strains and use that to calculate the progression of how the risk of 1 or more, 2 or more, 3 or more, 4 or more rib fractures changes throughout the test event. Johan will talk a bit about this as well. One of the advantages of using a probability-based approach is that since it all happens in post-processing, you can use the same strain output information to calculate things like how the risk would look across a range of ages or a range of people in the population. Because all you're doing is taking peak strains and comparing them against a local failure function and then combining the outcomes in a clever way. So this was an older example where our original local strain failure function was non-parametric, which is why it has this stair step. But you can take that local failure function and you can adjust it to target specific ages. And then for a singular simulation, you can use that singular simulation output information to sweep across ages and look at how the number of rib fractures would change depending on the target age that you're seeking to predict risk for. And we use the confidence interval approach on the left here, but you can also use that same approach to see how the probability of exceeding a threshold amount of fractured ribs changes as a function of age. All right, so probabilistic method summary, a combined probability approach. It's just one approach to take a wealth of information that you can gain from a simulation and condense it down to a simpler, singular measure of outcome. The limitations are that approach does not model fracture distinctly, so there's no change in load sharing that results from fractures. So you have to think about your application. If modeling changes in load sharing is important for your application, then a different approach would be needed. This approach also assumes that the fractures are independent events. So the coin flips are independent from each other. Fracture risk in one rib does not affect fracture risk in another rib. In reality, that's most likely not the case. In reality, fracture risks in individual ribs will most likely be related because they will be affected by the overall bone quality of the individual. And then in its original form, the method that I showed assumed that one local failure function could be applied across different models, meaning it could be based on actual cortical bone ultimate strain developed from cadaver tests. So just very briefly, one evolution of that process that we've been working on over the last couple of years is trying to accommodate that last challenge. So Johan's going to talk a little bit about validation of strain measures, and it's still good practice to try to get our human body models to output strains in a realistic way, or at a very minimum in a useful way. It's most likely important to have the strains be realistic, meaning within the range of natural human variation that'll result in a more robust model that we have more confidence in. But even with that, though, there's so much variation in the population that target, so getting the strains to behave reasonably, there's a fairly wide window that you can hit to meet that criteria. So two models can be judged as reasonably biofidelic, meaning within the realm of reason, within the realm of human variation, while still being quite different, right? And that's a bit of an issue. Well, so this is just one example of that. Two simulations run, one with the thumbs model and one with the GHBMC match simulations. Both of these are very mature, very well put together models, very well validated. But they still produce very, very different rib strains, right? So that's an issue because if we do try to apply a singular, consistent local failure function to both models, if they have different rib strains, even if those different rib strains are within the realm of human variability, we're going to end up resulting in different injury risk prediction, right? Which is a problem for standardized assessment. If we're going to use human body models for standardized assessment, it's quite important that we harmonize on injury risk prediction. So just a basic judgment of biofidelity, it's a good first step. But for standardized assessment with human body models, it may also be important to take an extra step and see what we can do to harmonize injury prediction, even though we're allowing flexibility in choice of human body models. So one way that we can do that is after developing and validating the model and verifying that the rib strains are at least reasonable, we can then tune the injury risk function for application to the specific human body model by running a large battery of simulations matching past cadaver tests. So this is very similar to the approach that we typically take for tuning injury risk functions for dummies, but now we're doing it for human body models. So again, it's important that the human body models are realistic and are biofidelic. But if we want to harmonize injury prediction to result in consistent injury prediction for standardized assessment, we can tune those local failure functions so that we have individual model-tuned, model-specific injury risk functions that end up resulting in consistent injury prediction when used in matched cases. So general process is we throw as much data as we can at the model. We run as many simulations matching as many past cadaver tests as we reasonably can. We take an optimization approach where we shift the local failure function to result in the best injury prediction compared against the past cadaver tests. And then we verify, ideally through comparing against an independent data set to verify that it's predictive at the end of the day. This is an example that we ran in a paper that we published in 2022, supported by Toyota, where we tuned the local injury risk function for frontal impact for the chest, for thumbs, and for GHBMC. And we ended up resulting in these curves here. So the thumbs curve was shifted to the left. The GHBMC curve was a little bit more similar to our starting point that we started from using rib cortical bone coupon test data. This isn't casting judgment on either of the models, right? So again, both models have been validated in their own way. This is simply saying that if we want to arrive at consistent injury prediction between the two models, this shows that they would need different local failure functions to result in consistent injury prediction. Final thoughts, since we're about at time. So this is just one potential method. This was originally conceived as a thought experiment, thinking about how to condense a large body of output information into a useful injury prediction measure. We've always been encouraging of further refinement, however, and exploration of alternative means. And there have been some very clever alternative means proposed recently as well. So we cannot assume a priori that the same local failure function would be applicable across all human body models. maybe it is applicable, but we shouldn't assume it from the beginning. We should at least check when applying any failure function to a new human body model that it is applicable, that it results in consistent injury prediction, and we should be open to the idea that it may require some tuning for that specific human body model, especially if that human body model is going to be used for standardized assessment in the mix with other human body models. And then even if the strains that are produced by the human body model are realistic, we still should validate the human body model across the range of use cases that it's going to be used for, meaning we should always be careful to check the predictive ability of the human body model and the injury risk function across the range of use cases, regardless of how the injury risk function was originally developed, tuning versus a ground up approach. We need to verify that the prediction is going to be accurate across the range of use cases where the human body model and the injury risk function will be used. All right, so that's all. So I'll turn it back over to Jobin. Again, thank you to Toyota and to Autoliv for their support, and thank you very much for the invitation to speak today. Thank you.
Thanks, Jason. I think, as you said in the beginning, let's have Johan's presentation also and take all the questions together in the end.
Yep.
Johan.
Yes.
Sharing. Yep.
Let's see. Am I sharing the correct or wrong?
Yeah, I can see your screen.
Is the correct one?
Yes, it's the correct one.
Okay, thank you for that. So I will continue now on Jason's, what he told you. I will focus more on the strain, what parameters that affect the strain, based on some work that I have been doing and that PhD students in my group has been done. So the agenda for this second part is that first of all, I will try to motivate the choice of the maximum principal strain for fracture prediction, especially for the rib fracture prediction now. Then after that, I will show that what human body model parameters that mainly influence the rib strain. And then finally, I will show how age is included in the current rib fracture risk prediction and what is not included. So if we start from the beginning here, in the original Forman 2012 publication, there is no mentioning of what strain component that should be used. However, in later publications, it has been said that the maximum principal strain, also called the first principal strain, is a good choice. The question is it a good choice? And in that case, why? To answer this, we will first step back a bit to the fundamentals of biomechanics. So if we look into the cortical bone, so this is an example of a femur. And if we zoom in on the cortical bone, we can see that basically it has one property along the length. This is called the osteons. And then it has other properties or another geometry or what we call it, other types of structures across this direction. These osteons, they form in the direction where we have most load. So they are based on evolution and daily based life. And in some cases, those loads can be aligned with the loads that we have in a crash, sometimes not. So that's not given that they will be aligned with that. So this structure means that cortical bone behaviors is orthotropic. So we have different properties in this direction and the perpendicular direction. It's asymmetric, meaning that it has different properties in tension and compression, and also viscoelastic. So we typically see some kind of strain hardening. So for higher loading severities or higher loading speeds, we see higher stresses that can be handled by bone. In human body models, we usually model this as isotropic, symmetric, and sometimes include strain hardening. and we use standard metal plasticity in most cases. So what do we really mean with tissue-based? And this was actually a question I got from a reviewer many years ago, where he said that you cannot say tissue-based because there are infinite many levels of tissue-based. Here we talked about like the global level of the femur. We can look at more localized level, and then we can go even down and down to the level of atoms. So yeah, what is tissue-based? It's not well defined. In the finite element method, we typically average the properties and the response of the material, in this case, the strain over an element. So we could also call it element-based fracture assessment. And this was actually suggested by the reviewer, but I responded that that sounds a bit had. Tissue-based is more what we mean here. We really want to distinguish this from a global criteria that we typically have in the crash test dummies that use a correlation metrics, for example, chest deflection, and relate that to what is happening on tissue level in the real human. So that is what we mean with tissue-based in this context. So if we then continue to look at the mechanical properties of the cortical bone, then what we see from mechanical testing is that cortical bone is stronger in the one direction along the osteons than perpendicular to the osteon direction. The Young's modulus, and this is a mix from different types of bone, mainly femur, I think. So it's about 30% stronger in, or the Young's modulus is about 30% higher in the one direction compared to others. Ultimate strength is 150% stronger. So it's much stronger in the one direction compared to the 2 and 3 directions. And the ultimate strain is also much, much higher. So it's more brittle, and it can withstand a much smaller strength in the 2 and 3 directions. The cortical bone is also stronger in compression than in tension. The Young's modulus in the one direction is about 5% higher
Johan.
in compression. Yeah.
Can I interrupt you? You have a pop-up on your screen.
That one you don't want to see.
No.
Sorry about that.
And
apparently I
if you
should do
could,
something now. Maybe present.
no,
Yeah.
you're presenting. It's okay.
No. Yeah. Sorry. Okay. Is it fine,
And
or
there's
should I
a-
move this one as well?
Yeah, that'll be good. Yeah, no, it's
Okay.
good.
Thank you.
Thanks.
So the Young's modulus is slightly higher in compression and tension, but more so we can see that the ultimate strength is about 50% higher in compression than in tension. Whereas in this study, they reported the ultimate strain to be actually lower in compression and tension. But I would say that that is more an artifact of the measuring, because that's the initial peak. But then in compression, the bone can withstand a lot of strain in a crushing fashion. So it's actually higher in compression than in tension, I would say. So what if we ignore all this information and model the cortical bone using a standard MAT24 that is isotropic and symmetric, which is typically done? Here we have some data from, which is basically averaged over Kemper data from 2005 and 2007. If we then use that for a model of a rib, so this is a setup replicating physical tests from Kinding from his PhD thesis, 2009. And this is bending of the ribs in the anterior posterior. So pure anterior posterior. So we hold this cup fixed and we move. Oh, you cannot see it because I'm pointing on the wrong ski. Sorry. And we move this box in the same direction, and we'll bend the rib. So if we do that, we can plot the maximum principal strains during that. And this is a simulation of one of his tests for rib number 7. And in this case, we can see that the maximum principal strain is about 1.7% at the end of the simulation, corresponding to when the rib fractured in reality. And I would say that 1.7%, based on the risk curves we have, that is kind of the onset of fracture risk for older subjects. So if we then look at the time for the fracture at the end of that simulation, we plot the maximum principal strain, or actually this is the maximum and the minimum principal strains, and we plot them as vector plots. We can see that the maximum principal strain is more or less aligned along the rib. And I didn't mention that, but the rib, if you look at the osteon direction in the rib, it's more or less aligned along the rib. So this means that we are actually loading the rib in tension here on the outside in the direction of the osteons. If we compare that to a uniaxial tensile test, which is what we do or what we have to create the risk functions, that would look something like this. You extract a coupon and you extract that along the length of the rib. If we zoom in on the material in this part of the material test, we can see that we have a stress state, or in this case a strain state, that is very similar to what we saw in the rib. We have the maximum principal strain pulling in tension here, and in compression, and then we have some compression here in the other direction. So if I go up here, you can see that we have tension and then we have compression perpendicular. The compression here is due to the Poisson effect. So when we pull in one direction, the Poisson effect results in that the material is pulled in the other direction. So the uniaxial tensile test here corresponds very well to the strain state that we have, at least in the anterior-posterior bending test. But in reality, ribs are usually not subjected to pure anterior-posterior bending, as they have an angle to the horizontal plane. And here we can look at some data from Sven Holcomb, published 2017, where he measured in the population the the pump handle angle. So that is the angle from the vertical plane to the plane of the rib. And we have that for rib 1 to rib 11. And we can see that it varies a lot in the population, from around 40 degrees to 80 degrees. We can see that it varies from rib to rib, and we can see that we have some significant effect of age. Here, the blue are the males and red are the females. So let's test what that means. So if I then rotate the rib to a 60-degree angle, which would be somewhere in around the average of the population, we run the simulation again, and we then look at the principal strain, or the principal strain vectors here. Now we can see that it's not following along the direction of the rib and along the direction of the osteon. So now we have rotated it a bit, and that means that it's not only loading in the in the direction of the strong bone, but also in the perpendicular direction that is much weaker. So in this case, there is a risk that we underestimate the fracture risk. Okay, so let's summarize the strain components here. The ribs are if they are subjected to anterior-posterior bending, the maximum principal strain lines up to the rib long axis, and it will also be greatest on the continuous, or the outer side. The maximum principal strain is therefore aligned to the strong direction of the cortical bone along the osteons. And if we also assume that the fracture will start on the tensile side, the continuous side, which is reasonable, as the cortical bone is about 50% weaker in tension or 50% stronger in compression, the maximum principal strain is then a good candidate for evaluating fracture risk in ribs. But for angled ribs, and the more angled you have them, the more shear you introduce into ribs, then the maximum principal strain will not be perfectly aligned with the rib axis. So if the maximum principal strain is rotated, we will underestimate the true fracture risk. So the second part here is about what you remember the model parameters that influence the rib strain. And in this context, parameters includes both global and local geometry, including the cortical thickness, as well as material properties, and then mainly material properties of the cortical bone. If we start with something simplified, so for a prescribed displacement, with the rib parameters defined according to below, so we have the arc chord length and we have the arc height length. Here we have a rotating end. No, I'm pointing the wrong screen. We have a rotating end here, and we have a prescribed displacement over here. We simplify the cross-section as an elliptic cross-section, so we have a width and we have a height of the cross-section. And we also approximate these cross-sections to be constant over the rib, which is not true in reality, but just for simplicity now. Then can be shown that the peak strain in the rib that will be here at the top of the arc, that is proportional to the height of the cross-section, so this smaller dimension of the rib, and also the global shape of the rib. So we can see that we do not have any material parameters here, so it's for a prescribed displacement, the material doesn't matter. On the other hand, the rib force is proportional to Young's modulus, so here we only consider small deformations. So here we have the material, and here we again have the height of the cross-section, but it's cubed. And then we have the global parameters. So the force, and therefore the stiffness of the rib, is dependent on the material. But for a prescribed displacement, the material does not affect the peak strain. So if the ribs would carry all external force, the rib deformation and therefore the rib strain would be dependent on the rib geometry and the rib materials. And then we could call that the force control system. The other thing, if the ribs would carry only a minimal part of the external force, then the rib deformation and therefore the rib strains would only depend on the rib geometry and not the material properties. And this would then be a displacement control system. And this has implication for what parameters that are important to accurately capture rib strains, but also for how we model age dependency, which we'll come back to later. So is an actual chest load then force or displacement control? So we can look at an example here. This is one of the HBM for VT load cases. This is a Kent tabletop where we have a cadaver on a table, and we have a belt, diagonal belt, that is pulled over this cadaver, deforming the chest. What we can see in this case is that the energy, the internal energy in the ribs is about 25% of the total energy that is absorbed in the whole human body model. So this means that we are somewhere in between force and displacement control. A pure displacement control would be if this energy in the ribs would be close to 0, and a pure force control would be if it's close to 100. But clearly here we are somewhere in between, but maybe closer to the displacement control. And the reason for this is that we have a lot of other structures that will also carry load. So we have all the intestines, and for example, and these are viscous, so the higher the load, the higher the loading rate, the more load they can carry. We can also look at the more realistic case. So here we have an inertial load case. So we have a human body model in a generic buck. So this one would be quite realistic. We have a seat belt, force limited seat belt, and we have an airbag. In this model, we varied many parameters. So we varied the overall rib cage shape using a number of principal components. And you can see especially here, the first one is basically the angles, this pump handle angle on the ribs. The second one is the depth of the rib cage. and then we had a few others. We also varied the cortical material according to a realistic range. So all this variation is based on population data. So we are varying it according to plus minus 1 or 2 standard deviations. I don't remember what we used. It's actually 2 standard deviations as here in the population. So we vary the material parameters in the cortical bone. We vary the cortical thickness. So what you see here is the distribution. So these are different human body models with different distributions of the cortical thickness. So we have a cortical thickness going from 0.1 up to 3 millimeters, but it varies in all the different human body models here. We vary the rib cross-section, both the width, and if you are really paying a lot of attention, you will notice that we have flipped the definition here. So if you go back a couple of slides, then they are flipped. But now we call this the width instead of the height. The trabecular material, as that is kind of supporting the cortical material. And then we also changed a couple of other materials that will transmit the loads to the ribs. The result of this was that we found that 3 parameters are more important than the others. The first one is the rib cortical bone thickness. And again, we have varied all the parameters according to what is seen in the population, so they should be comparable. The rib cortical thickness is actually the most important one here. This is a sensitivity index, so the higher that is, the more important the parameter is. The second one was the rib cross-sectional width. So that is the smaller of the 2 axes in the ellipse-shaped rib. And then finally, the rib cortical bone material. These are the 3 most important parameters. So next we can have a look at the current or some of the current human body models, how they model the ribs. And this is from a recent study by Sven Holcomb, 2023. What we can see here is 2 examples. The top row and the bottom row are examples of 2 individuals that are quite close to average male. Then we have the cross sections of the VIVA Plus, the GHBMC, and the thumbs version 4 in this case, the shape of the cross sections. We could notice, so here, in this case, the thumbs model uses a constant thickness of the cortical bone. The GHBMC uses variable thickness, and actually the VIVA Plus also uses variable thickness, but there was an error in this manuscript or this paper. There is an error in this paper, so Sven calculated this as a constant thickness. So basically the curves that I will show on the following pages are not valid for the VIVA Plus model. So if we then start by comparing the total area, so that would be, this is the outer surface of the cortical bone, and then if we take the total area inside, what we can see is and if we ignore the VIVA Plus because they are wrong, so if we look for the upper ribs here, the 2 to 6, we can see that the GHBMC has maybe slightly too high area here for the upper ones, but then for the lower ones, it's pretty good. The thumbs model is a bit higher, so the total area is a bit bigger, and the total area is roughly proportional to the width and the height. So this is an indication that maybe the width and the height is a bit on the high side for the thumbs model. And in this case, I can also say that the gray area represents plus minus 1 standard deviation, so about 66% of the population. So we could make it twice as big, and then we have 95% of the population, which is a reasonable number to compare to, I think. If we look at the cortical area, we can see that I would say that the models are quite good here. The lower ones are more or less inside the corridor, most of the upper ones as well. So all of the models, or at least the GHBMC and the thumbs, because we cannot really compare the VIVA Plus, probably have a decent representation of the cortical thickness here. And then when you combine this into the bending moment and inertia, and now we look bending over this axis, the weak axis, then we can see again here that the GHBMC model is maybe a bit on the high side for the lower one, but and then quite good for the lower ribs here, while the thumbs model is a bit on the high side for the upper and very high for some of the lower ribs here. So this indicates that maybe I would guess that this dimension in the thumbs model, if we go a couple of slides up here, so this dimension here is maybe a bit on the high side for the thumbs model compared to the population that Sven Holcomb looked at. And maybe we can even see that if we compare here the three models, at least for rib 8, one of the lower ribs. So by adjusting the human body model parameters to be realistic, preferably close to the population average, we would expect predicted rib strains to match the strains measured in the PMHS test. And we could actually test this, and this would actually then be the validation of the metric that is used for the tissue-based rib fracture prediction, which is a strain. So for the SAFER HBM, we have done this in the past, and we have done this at different complexity levels. And of course, then you need to find cadaver tests that are instrumented with strain gauges, because the strain is what we're going to compare here. So one example here is Kindig. So during his PhD, he did this isolated ribs in anterior posterior bending. He had 6 strain gauges, and by simulating this with, in this case, the generic ribs from the SAFER HBM, we could show that the red dot here is the result from the simulation model, falls within the interval of the tests. And actually, to be fair, those are very huge, except for some spots here. But this is at least the first indication, so we are kind of in the middle of the range here from the physical test. Then you can move on. So you increase the complexity of the external loading. So we call this body region level. And this is yet another test that is part of the HBM for VT test. So this is a tabletop test from Shaw. In this case, we have a metal surface here that is impacting the sternum. And we can again compare the strains. We had a number of strain gauges here from rib 3 up to rib 10, both on left and right side. And we can compare the red curves with, in this case, we only have 2 tests, physical tests. So it's a bit limited to create the corridor. We need to acknowledge here that in the HBM, we don't have an element erosion. As Jason told you, we are doing this in the post-processing. So we're evaluating the risk in the post-processing instead of having element erosion. So basically, there's no meaning to compare the curves past the point where we have fracture in the physical test here. And then finally, there are a few full cadaver tests with more realistic boundary conditions. So this is Shaw 2009, also one of the HBM for VT tests, where we have a belted occupant without any load limiter. And in this case, they had 4 strain gauges on each side, and we could compare the traces from the cadavers in gray with the simulation result in red. And again, there is a widespread in the cadaver test, and I would say that we do a decent job here at least, but it's really hard to say if it's perfect or not. So a summary of the parameters influencing the strain. The loading of the rib cage in a crash is somewhere in between a force and displacement control system, with only a limited portion of the external load carried by the ribs. The most important HBM parameters influencing the rib strains and therefore the fracture risk are the cortical thickness, the rib cross-section width, the smaller of the two dimensions of the rib, and the rib cortical material properties. Comparing human body models to population rib cross-sectional data shows that the GHBMC matched the data reasonable, while the thumbs version 4 model seems to be a bit wide in these smaller to the dimensions. And I think this could be one of the reasons that the injury risk function needs to be adjusted more for the thumbs model than for the GHBMC model, if you could remember the two adjusted risk functions that Jason showed you earlier. So my suggestion here is to make sure that the human body models are within the population corridors, at least for the important parameters, and preferably to validate rib strains using available cadaver data. And I think if that is done, that would result in minimal injury risk function tuning needed. Additionally, this would be important for morphed human body models, as otherwise each morphed human size would need to retune the injury risk function. Okay, then the third topic is how is age included in the current rib fracture risk prediction and what is not included. And what we can start with to say is that age is correlated to many aspects of the rib properties, including the overall shape, the cross-sectional properties, including some thinning of the cortical bone. But here we will focus only on the material properties. So in the original Forman 2012 publication, the risk function was age adjusted based on femur data, because we didn't really have a lot of rib data. So in that case, that femur data showed a 5% reduction of strength per 10 years. The big limitation at this point was that we only had data points or data from 12 cadavers. And actually, those are the 12 steps that you can see in this empirical function. Those represents the change in risk for these 12 cadavers. Even more importantly was that as all cadaver tests, it was biased towards elderly, so that one subject was 18 years old, while the rest was 42 or more years, or higher years. And I think that was one of the main reasons why Forman decided to use age adjustment based on the femur data. Later on, more data has become available. So here we have tensile coupons from 58 cadavers with age ranging from 70 to 99 years old. And based on that, an updated injury risk function was created using survival analysis. And survival analysis compared to the empirical data also is good because that will give us smooth risk curves instead of the stepwise changes. And here we can see that we have an age effect. So the blue curve represents 75 years old, and that we can see that the onset of fracture then is less than 1%. The black one is for 50 years old, and the red one is for 25-year-old, and then we can see that the onset kind of is moved up to 2%. A note about this data is that the data is based on subjects with sufficient bone quality to enable fabrication of coupons. So I know that when they did this, they had some coupons that broke before they could test them. They were too fragile to handle. So this means that the age effect is probably underestimated for the oldest age group, because that it was basically very hard to create coupons from some of these subjects. So the typical stress strain curves was published in Katzenberger here for different age group, and what we can see here that we start with the yellow one, teens, then we go to 20 years old and 30 years old. So we can see that the stiff or the strength of the ribs increases, and then from 40 years old it starts to drop down to 90 years old. That is one thing. We can see that like the yield surface here moves up and then moves down. Another thing we can see that for each decade here, the ultimate strain decreases. We can also plot this in this form, which was done in Katzenberger. Hope I didn't miss this reference now. So here we can see the Young's modulus, how that changes over age. We have the yield stress, we have the yield strain, which does not change a lot. We have the failure stress, and then we have the failure strain. So in the current implementation, the age is only adjusted based on this. So if we now remember that for a force displacement control system, the material properties will not influence the strain. And we also remember the ribs are somewhere in between a force and a displacement control system. If the material properties don't matter or doesn't decide how much strain we get, well, then the modulus, the yield stress, the yield strain, and the failure stress are not really important. So speculating, this might be one of the reasons age effect is actually shown to be captured really good compared to population data. If we then summarize this section on the injury risk functions, so human cortical bone properties varies with age, including global and cross-sectional shape, thickness of the cortical bone, Young's modulus, yield stress and strain, and ultimate stress and strain. In the current rib fracture prediction, only one aspect of these are included, and that's the age dependency of the ultimate strain. The main advantage is that only one model, typically with average material properties, needs to be run, and the risk for fracture can be estimated in the post-processing for multiple ages. The main disadvantage is that in reality, the weaker material of the older occupants would, if they would be included in the model before we start the simulation, to some extent result in higher strains. And that means that we probably underestimate the true effect of age. And then some final thoughts here. So despite all the limitations, or the limitations that I highlighted today, the framework has shown to predict rib fracture risk accurately. And I can mainly then talk for SAFER HBM because that's what I've been working with. We have previously done matched outcomes with 22 detailed real-life reconstructions, and we saw very good predictive power of this of the rib fracture risk. We also lately now have done, so we have some unpublished results that hopefully will be presented at ESB 2026, showing an area under the curve of 0.9 for frontal impacts and 0.84 for side impacts, and these are for number of fracture ribs 2+. So for you who don't know what an area under curve is, that is a measurement that can vary between 0 and 1. And if you have a value of 0.5, that is basically a flip of a coin. So you have a model that doesn't know anything. You just by pure chance get a result. Then you will have 0.5. If you get 1.0, then you have a perfect model that capture all the aspects. So here we show that we could get 0.9 for frontal impacts and 0.84 for side impacts, which, yeah, according to us, means that it's a really good model to predict the risk for rib fractures. Specifically for human body model developers, make sure that the rib cross-section width, the cortical thickness, and material properties match population averages. Preferably also validate the rib strains at multiple model complexities. And personally, I think that this will result in minimal injury risk function needed at a later stage. And we talked about that only one of all age-related changes to human ribs are currently accounted for in the tissue-based rib fracture prediction. And future studies should investigate if additional parameters are important for accurate estimation of age effects. For other body parts that are loaded in a more 3D stress, so we could see here that we had the maximum principal strain aligned along the ostium direction in the rib. So that's more or less a 1D stress state. But if we have a more complex structure with 3D stress states, pelvis, for example, then the use of the maximum principal strain derived from tensile coupon testing as to be used as an injury might give poor predictable power. And that the reason for that is the fracture will probably be initiated in one of the weaker material directions. And here are the references, and that was all for me. Can move up to the references again.
Thanks, Johan. Yep, I think we can now open up for questions from the participants. And if you have questions, you could write them down on chat. As this is a webinar, WebEx, I don't think participants can unmute yourself. Or maybe you could. Oh, I guess you could request an unmute if you would like to speak. Looks like the presentations were super clear. No questions, Johan, Jason. That's excellent.
There is one question about the participant count today, which is not really about the technical content, but I think it was 43 starting and now it's 38.
Yep. For the curious, yeah.
So maybe I'll throw a rock in the pond here and ask Johan a question. So
Yeah,
Johan,
and I have one for you later. Yeah.
Great. What do you see as the big next step, right? What do we still need to tackle to take the next step?
There could be many next steps. One next step is that in some cases we have posterior rib fractures. So I think the current framework in frontal impact, mainly where it has been validated, seems to work very well. I was actually a bit surprised that based on the AUC, we saw almost similar prediction power inside impacts, even though we haven't really validated the model inside impact. We have, however, other loading conditions, for example, high-speed rear-end impact, where Kang from Ohio State has shown that we can get posterior fractures. And also we see posterior fractures in some motorcycle accidents. I think those can be a bit more tricky for one reason, because I don't think the ribs are super biofidelic in the posterior region. That varies, of course, from model to model. So I know in the SAFER HBM that is at least something that we can work more on. So I'm thinking to catch those is tricky. Another thing that I have been struggling with for many years, that is it possible to also predict the fracture location? And that is a hard question. And one way to test that, we modeled really detailed ribs long time ago, and I know that has been done at UVA as well, to capture small effects. So basically you use solid elements to model the cortical bone, so several layers. So it's really, really detailed model, not suited for full HBMs. The results was a bit mixed. So what we could see that, yes, we could capture the fracture location for about half of the ribs that we tested. And what was common between those, but that they were generally a bit younger, of better quality, cortical bone quality. And then half of the sample was older subjects with presumably more pores in the cortical bone. So the hypothesis is that we do have pores that we don't really see in the CT data that is used to develop these detailed models that will get you a stress concentration that will give fracture at locations where we don't really see the highest stresses or the highest strains in the like bulk material that we model. So that is still very challenging, and it might even be impossible to get that into the full body HBMs, at least in 10, 20 years or something like that. Partly because we need very detailed model, and partly because it's probably very stochastic, where you have those pores.
Yeah, and I think that's a great point. It brings to mind a conversation that you and I have had a lot, where none of this, at least in my mind, none of this is universal. We always have to be thinking about what's the specific application in question that you're seeking to address whenever you're running a model or trying to predict injury, right? So if your application is I'm trying to model the actual mechanics of injury so that I can understand more about how rib fractures actually occur in a person or in a set of the population, or how they are affected by things like person-to-person variability or differences in soft tissue thickness or whatever. If your question is fundamentally trying to understand the underlying real mechanics, then yeah, these sort of considerations are very, very important. What are the factors that are actually contributing to the occurrence of fracture, be it interperson variability, local imperfections? I agree is probably a huge one and very hard to capture. But alternatively, if your question is more, I'm a restraint engineer, and I need to run a simulation sweep to try to optimize my seatbelt system, then that's a very different question. And then you need a model that maybe has been developed as a standardized tool, right? And something that gives you a reasonable prediction of overall severity of the loading and reasonable prediction of overall fracture risk, but in a way that is usable from a fundamental engineering approach, right? So much less of a biomechanical understanding tool and more of a practical, I need something in my environment that is going to give me useful information, but in a fairly standardized way that I can use in a straightforward manner.
Yeah.
So those are two very different things. Yeah.
Yeah. So maybe if I can follow up on that.
Yeah.
You're totally right. And I mean, there are applications where this could be, what I highlighted could be interesting if you do reconstruction, case reconstructions, if you work with forensic or something like that, where you really would like to predict what actually happened to that individual. Personally, I think that is very difficult, if not impossible, because we typically we will never have enough data of that specific subject. Another thing that came to my mind when you talk here is that what I think we are missing, and I touched slightly upon this, is a good representation of the most fragile in the population. So if you're going to create a system, if you're going to optimize a system and you want to optimize that for the entire population, then I think we are missing information about the most fragile. We see that when we do subject specific or cadaver specific models, some of the cadavers we cannot predict at all. we predict 0.0% risk, and they get like 10 fractured ribs. So something is very off. They could have severe osteoporosis or something, but our material curves, even if they are age adjusted, does not correspond to the actual risk. So I think we are missing something there, and I touched upon it. One reason could be that we cannot create coupons out of these most fragile individuals, so we don't have them in the design of the injury risk function. But there could be a lot of other things as well.
Yeah, I think in your discussion, you both answered two questions partly, but maybe we could bring up the questions that came up. Son asks, can Jason Johan share what the roadmap look like for enabling restraints design optimization using multiple available HBMs and workflows from this point forward?
Very good question. That's going to take an industry-wide collaboration, I'm sure, to figure out how to standardize these approaches. Because yeah, there's fundamental biomechanics considerations. There's also usability and standardization considerations as well, which are a very practical thing that would need careful thought to address. So if anybody is interested in putting together a task force to develop such a roadmap, I know I would certainly be interested in participating. And I see Johan nodding his head as well.
Yeah. Definitely. And it could be some, I'm sure we will do something in the HBM for VT, but I can also see that we can do it on another level, more international level than that also.
Thank you. And Manu Agarwal has a question. While calculating the fracture probability values for minimum X fractures, is it useful to disregard those ribs which have probability values that are closer to 0?
And that, I think that speaks to the cumbersome nature of the combined probability approach. So we have developed a way to streamline the calculation of the combined probabilities. It doesn't end up disregarding zero values, but it does end up vectorizing the information, so the calculation is a little bit more efficient. And I believe that we provided that. Maybe it was to the group that was developing Dinosaur, and potentially the TUC group as well. But we do have some code that has a slightly more efficient approach, just using more efficient vector math to accomplish it.
Yeah. If I should comment that, I'm not sure I understand the question correctly, but if the rib has close to 0 risk, it doesn't really contribute to the overall risk for 2, 3, 4. So you can just by looking at the probability for each rib, you can kind of see if it will be a high or low risk for 2+ or 3+, because usually it's dominated by a few ribs that have maybe 2, 3, 4% strain, and those will contribute a lot to the overall risk to 2+, 3+, or 4+ risk. So the ones close to 0, they don't really contribute. So they are filtered out by the method, sort of.
Yep.
Yeah. Thanks, Johan and Jason. I think we are running out of time, so maybe we can wind up with a general question that moves to anywhere in the human body. David asks, how applicable is this same strain-based probabilistic approach to bone fracture elsewhere in an HBM, for arbitrary load case? Ideally, someone should be able to use risk versus injury risk curve to
it's a great
predict.
question. So we've always wanted to see the same combined probability approach used elsewhere in the body. Jeremy Perez from PDB took not a combined probability approach, but the same sort of tuning-based methodology that I showed later on. He applied that to the pelvis, which was very encouraging. I think that structures like the pelvis that are like the rib cage, where you have a complex structure with multiple potential fracture sites and multiple potential strain hotspots, I think that's a good candidate for also doing the combined probability approach. And we may be having a try at that here in the next year or so. But yeah, I think any place where there's a challenge with taking a large amount of information from the output of the model and trying to condense it down to a single understandable output measure that can be used for some purpose, I think is a good candidate for maybe this type of combined probability approach.
Yeah. One thing that we need to consider is that in this approach, at least in the current implementation, we assume independence. So that can affect if it's feasible or not. One example is that I've been thinking of this for the spine, for example. But the thing is, if you have like an actual compression force of the spine, could we say that they are independent events then? If one vertebra fails in fracture, does that not change the loading to the other ones, or does it? So in some cases, it can be that this independent assumption cannot be fulfilled. So, and then I guess maybe there are other methods that I don't know of that can be used.
Yeah, interesting discussion. I'm sure we could keep going on.
Yeah, sorry for
but
taking so long in the presentation.
No, I think it was good. Hope to continue these conversations in other venues, hopefully. But thanks everyone for joining, and thanks to Jason and Johan for putting effort into making the presentations, and nice discussion.
Yeah, and I will say, if anybody's interested in carrying on the discussion, feel free to email me as well. I'm sure Jobin can provide contact information.
For sure, yes.
Same for me. Yeah.
Yep. Thank you. Thank you, Jason.
Okay.
Thank you, Johan.
Thank you.
Thanks, everyone.
Thanks so much, everybody.
Bye.